There's another reason that physics is difficult, and it's because when we're doing physics, we often can't describe things exactly as they are. We have to do what's called building a model. So I'll give you an example. Let's say we have something like a baseball, okay? And let's say, that baseball is made up of a number of atoms and molecules, and, there's all of these little particles that make up a baseball. Okay? And then let's say that baseball's falling toward the ground, and the ground is also, made up of all sorts of different particles and molecules. Well, not only that, but we also have the air. And the air is a whole bunch of different particles and molecules all, bouncing around and interacting off of one another. So let's say that we could actually describe this. Let's say we could actually track all of the individual atoms that make up the baseball, and all of the individual atoms that made up the air, and all of the individual atoms that make up the grass. Can you imagine how phenomenally difficult that would be? So we can't use the theory, that talks about small objects, which is quantum field theory. That's not going to work because it's just too complex. Even the most powerful supercomputer, ever built, couldn't even begin to do a calculation like that. So instead, what we have to do is we have to build a model. So a model is an often simplified picture of a system that discards relatively small effects and tries to keep the important ones. Now, how good a model is depends on, how good of a job you do of figuring out what's important and what's not important. And so, for example, in a case with a baseball, falling toward the earth, if, we actually can't really neglect air resistance for the most part because that's a very important effect. And you notice that the trajectory of a baseball changes very differently because there's air around than if there wasn't. But on the other hand, if we look at something like a satellite that's going around the Earth, where the atmosphere is much lighter there, and there are fewer air molecules for the satellite to bump up against, then we can, to a very good approximation, completely and totally eliminate the air. So the model we use depends a lot on the system that we're looking at. But again, often we're looking at a much more simple model than this actual case of the particles that are actually making up a system. For example, we could have something where we have a ball rolling on the ground at some velocity, and we'll look at the forces on it, and we'll talk a little bit later about what a force is. But you can kind of have this idea from what we've been talking about already, that it's going to have to do with interactions, and forces are something that interact with particles to change their motion. And so we'll say, well, we'll just call this one thing the frictional force, and there's another force, forces on it that are due to air resistance. And so we'll call these, just a drag force acting on it. And that drag force is going to be something, proportional to some constant b times the velocity or the speed of the ball squared. Okay, and this frictional force, we're going to say that's about the mass of the object times the acceleration due to gravity times this coefficient of friction that's different for each surface. So again, we've gone from this picture where you actually have a ball made up of all these little tiny molecules bumping up against the ground, to a couple of very simple equations that to a very good approximation will tell us exactly or approximately how the particle is actually moving and interacting. And I think one of the most difficult things to realize when you're learning physics is that this is the way the world really works. There's really next to nothing that we know exactly. Everything that we do, every experiment that we make is always an approximation. And the better the experiments get, the better the theory can become to describe it. But realistically, we can't talk about anything. Anything. The interactions, even the very complicated things that go into building your computer, are not exact. They're approximations, but they're very, very, very good. And it's because we've had about 400 years of people building models, and each time somebody comes up with a little better model. And when they do that, we get to benefit from that because it makes learning physics easier, and it makes the things that we can build with it and do with it easier.